Hi there. Kubernetes Health Checks. What are they for and why are they useful? And what is the difference between a liveness probe, a readiness probe, and a startup probe? These are probably very abstract concepts to you. So, before I go straight into explaining these concepts, I think it is better that I share a story from my time as a Java developer. At the time when Kubernetes didn't exist yet. It was in the year of 2009, at the time of the iPhone 3GS, which happens to be my first iPhone. It was also the first year when Bitcoin came into place. It was then that I finally got my big chance working for a very cool fashion brand in the heart of London. I was in a very cool team and I was doing their brand new redesigned website. We were using JBoss as our Java application server and coding in the best programming language at the time, Java of course. We had 4 application server instances, 2 in each data center, 4 web servers, 2 in each data center, 2 database servers, 1 in each data center, and a load balancer serving traffic across all the instances. We are also using Akamai for our CDN. After many months of hard work and exhausting days, we finally managed to complete the development of fashionarras.com. So the go live day was scheduled. And then party time came. In fashion, the party was surely going to be the best, right? Okay, for those of you who have a fertile imagination about how parties in fashion may look like, I have reenacted this party exactly how it happened, so you don't have to imagine anymore. Hello? Hi boss? Sorry, can you say that again? I can't hear you. I'm dancing with the team, celebrating the go live. Why are you not here, boss? We're waiting for you. What? The website is down? You're joking, we just launched the website. How can it be down? Oh. So we went back to the office and logged into each server. Each server seemed to be working fine for a few hours, and then all of a sudden started throwing all kinds of exceptions and grind to a halt. This was a very strange problem because it cascaded quickly to all the servers. We suspected it was a memory leak, but we had no clue where the source of that memory leak was. So in agreement with the operations team, we decided to monitor the logs, and as soon as the error showed up again, we would restart all the servers. This bought us some time, and eventually we figured out that every 3 to 4 hours the issue happened, so we created a script, a simple bash script to do an automatic restart of the servers. But this wasn't always working because sometimes the crash happened within 1 hour of a restart. Not great for our sleeping schedule. Also during the restart, the load balancer still sent requests to the server restarting, so some users would see a broken page on the website. But the point of telling you this story is just to give you a context on how everything could have been different if we had Kubernetes and health checks. So I'm going to go back in time, not literally, and implement Kubernetes health checks. First, let's change the architecture. Now, instead of having 4 physical servers in 2 data centers, we have a GKE regional cluster with 3 control planes and 9 worker nodes. 1 control plane with 3 worker nodes in each zone. A zone in GCP is a separate data center for all intents and purposes within a GCP region, and each control plane and each worker node are separate VMs. And now we can expose our website using an ingress that is connected to a GKE load balancer. The fashionarras.com website has 9 pod replicas with JBoss running in each worker node. We are using a managed MySQL database with high availability, so we don't need to worry about it too much. To ensure that our JBoss pods are restarted every time the pods stop responding to requests, we need to define a liveness probe for the JBoss pod. But what is a liveness probe in Kubernetes? Glad you asked. A liveness probe is a health check provided by Kubernetes to check that each container inside a pod is healthy. The liveness probe gets called periodically by the kubelet, and if a liveness probe comes back with the status of error, then the kubelet will automatically kill the container and restart it based on the pod's predefined restart policy, which normally says to restart. There are three types of liveness probe: TCP, HTTP, and command. The TCP liveness probe regularly attempts to open a TCP IP connection on a given port. This can be useful to do simple liveness checks for containers that rely on TCP, for example, FTP. In this example, we can see a TCP liveness probe that checks every 10 seconds port 21, which is the port normally used by FTP. We didn't specify the success threshold, but we know it will default to 1. This means that every time a valid TCP IP connection on port 21 is established by the health check, then the container is considered to be alive and well. On the other hand, we have increased the failure threshold to 5. So in this way, the odd failure in connection doesn't immediately trigger a restart of a pod. The HTTP liveness probe is a simple probe that makes an HTTP GET request to an HTTP server running inside the container on a given path and port. If it returns a 200 OK, it means that the container is alive and well. Any other HTTP return code means that all is not well with the container, so after a number of failed attempts, the kubelet will attempt to restart the container. Sometimes it's not straightforward to know if a container is ready to receive requests. For those special cases, Kubernetes has the command liveness probe. The command liveness probe gives us complete control on how to do the health check. We can use any command available within the container. For instance, we can check the contents of a file with cat, or we can even write our own script, which is included in the container and executed by the command probe. Okay, now enough theory. Let's try to create the liveness probe for the FashionArra's website, which have already migrated to Kubernetes. For the JBoss container, since it accepts requests on port 8080, we need to set up an HTTP liveness probe that targets port 8080. There are some important parameters we are passing. Let's start with the success threshold. We set the success threshold to 1. This means if one HTTP GET request returns 200, the GET request is successful. We set the failure threshold high enough that even if the liveness probe fails up to, in this case, 5 times, the default is 3 by the way, it will not cause the JBoss container to be immediately restarted. This parameter will depend, of course, on the robustness of the application and the likelihood of it failing from time to time. If too low a failure threshold, then we could have quite a few restarts of the pod happening, causing even more problems. The timeout in seconds is an important parameter. We need to have an idea of the typical response times of our JBoss container for this page. If we set the timeout too low and the typical response time exceeds the value set in timeout in seconds, then we are going to have serious problems as the container will restart continuously. Java is slow and it takes at least 30 seconds for the JBoss application server to be immediately available. Well, immediately is the wrong word. For that reason, we set an initial delay seconds of 30 to ensure that the kubelet doesn't call the liveness probe too early before the container is ready to receive traffic. Now, thanks to the liveness probe, the fashionarras.com website is going to stay alive even if our pods crash, as the kubelet will restart them automatically. Isn't that great? We just have a small problem. It takes at least 30 seconds for a new pod to start. And while the pod is starting, any traffic directed to that pod will fail. We can fix this by setting up a readiness check. A readiness check is very similar to a liveness check, except that the kubelet doesn't restart the pod even if the readiness check fails. Anytime that the readiness check fails over a failure threshold, the pod is removed from the list of pods that receive requests from a service load balancer. And when the readiness check succeeds over a success threshold, the pod is added to the list of pods that receive requests from a service load balancer. One of the drawbacks of readiness and liveness proofs is that they are independent of each other. For instance, a readiness proof might be patiently waiting for a container to be ready, but the liveness proof may kill it before it becomes ready. For slow starting containers like Java processes, this can be a problem. Wouldn't it be nice if there was a proof that could disable temporarily the readiness and liveness proof until the container was ready? That's why the startup proofs were introduced recently, to wait for a container to be initialized and ready for receiving new requests. So let's add a startup proof to our Kubernetes configuration. The startup proof looks very similar to a readiness proof or a liveness proof. And the main goal of the startup proof is to give enough time to slow running containers to start by disabling all readiness and liveness proofs until the startup proof succeeds. In this configuration, we created a startup proof to check every 10 seconds if the container is started successfully. We set the failure threshold of 30, which means that if the container doesn't start within 300 seconds, the pod will be marked as failed. If the proof succeeds at least once, then the readiness and liveness proof will be enabled and everything proceeds as normal. And that's it! We have turned our fashionRS.com website around by using Kubernetes Health Checks. If it was today, I would have slept soundly and maybe I could still be dancing. I hope you found this video useful and don't forget to smash the like button, and I hope to see you again soon. Happy coding!